Hello everyone, and welcome to EEL 3004 Linear Electric Circuits 1. My name is Reza and I will be teaching this course throughout this semester. This is a mixed mode class, meaning that a majority of the lecturing is going to be through video lectures online, and when we meet in class face-to-face, we usually review your questions about the lecture and do problem solving. By now, most likely you have met me in class at least once, and this is the first lecture which we're going to start covering the material from the first chapter of the book. Make sure that you watch these lectures ahead of the time before the face-to-face meeting, and it's important that you pay attention when you watch these lectures, and once you're done, you actually have to submit a short assignment. The assignment is basically submitting your questions about the lecture that you just watched, so that shouldn't be a big deal. It's natural for you to have questions once you're presented with new material, but I'm hoping that through that process you gain more out of the face-to-face meeting, because you come in with the questions and we try to answer your questions during the face-to-face, and we also do a lot of problem solving during that time. The book that we're going to use is this, the Electric Circuits. It's the 11th edition that we're going to use for assigning homeworks. So if you happen to have any of the earlier editions, in terms of the material is going to be pretty much the same. There's not much that is going to be different when you're introduced to circuit analysis for the first time. But the only thing is that there's a possibility that the question numbers are different from one book to the other. So if you happen to have an earlier version, you do want to check the questions at the end of each chapter to make sure that you are actually trying to solve the correct problems that are assigned. The kind of questions that I expect from you are conceptual. I think that the questions like how something works or why we do something the way we do are fundamental in directing you toward a better understanding of the topic matter and subject matter. And if that's what I expect of you, I actually try to practice that in my presentation of the material. In a sense, I would try to explain to you each time that we do something, why are we doing something and how exactly we're going to do it. Starting from the most basic, that is, why do we care about electrical circuits, specifically as electrical engineers or computer engineers. Why do we care about electrical circuits and circuit analysis? So there's no doubt that electronic devices has made a huge impact in our daily lives, and the way that these devices are now integrated in our life is so that we basically can't live without them, and in a sense, any of the machines that we use to help us in our daily lives, the language or the domain of energy that is most dominant in the operation of those devices is the domain of electrical energy. And therefore, to understand how these devices operate and how to first of all understand their operation, secondly being able to analyze their operation and do basically fix any problem with a system of electrical devices, and lastly, at a deeper level, to be able to design a system and manufacture a system, we need to be able to do circuit analysis. So I guess it's a good time to actually explain what a circuit is. So there are electrical components, and each component on its own usually doesn't give you any useful functionality. The useful functionality of these components comes about when you start putting them together in a network, at which point you can actually design them to do something useful for you, useful work. So these are some of the examples that are in the book, very simple examples of electrical systems that we use in our daily life, starting with the electrical energy distribution inside a house for lighting purposes, for example. So in this network, each one of these boxes could represent an electrical device that functions inside the house, including light bulbs. And once you connect them in a certain way and you connect it to an incoming energy source, then you can operate them properly. And examples of these devices that are connected in house, you can see them everywhere, including in your kitchen. TV is another example, and you can think of any other electrical device in the house. Now, proper operation of these devices requires delivery of enough electrical energy to each system, and delivery of enough electrical energy to the whole house as a system, and being able to control that delivery of energy also is an important component of this specific application. And you can think of any other electrical system for that matter. And this is a larger scale system. Now you can think of other systems such as, for example, your cell phone, or a telephone system is shown in this picture, where you can get connectivity to any other telephone in the system, or cell phone in that system for that matter. And this is a larger scale electrical system that we are used to use daily in our life these days. So I guess I'm going to skip more of these examples and kind of jump into, by the way, these are important, and they're explained in the first chapter of the book. These are the units for some of the physical quantities that we're going to use, and these are the main units in the International System of Units SI that the book is going to use. But I'm not going to go over them, and I'll leave that to you for your review, and we're going to only start using them as the need arises. This is also important, the prefixes, to know what each one means. It's good for you to know these prefixes and what they mean. In case you don't know, you can always ask me during the class. A couple of examples that are important. Kilo symbol is K, and it's 10 to the power of 3. Mega is 10 to the power of 6. Giga is 10 to the power of 9. And then the other way around, milli is 10 to the minus 3. Micro is 10 to the minus 6. And nano 10 to the minus 9. These are the more common prefixes that we use. Now, I'm going to jump to this part of the book, which is, to be honest with you, one of the most important concepts that you need to understand before we can move on. So we discussed that there are electrical devices that we use day to day. For example, a light bulb, is an easy example to deal with. Now, when you want to understand the functionality of that device, say a light bulb. I'm going to draw the light bulb here. So this is basically a schematic representation that kind of looks like a light bulb. But if every time that you want to analyze a circuit including this device, you have to draw this device in your circuit, that would be really time consuming, and it's not an efficient way of dealing with the analysis. So instead of drawing the actual device, what normally we end up doing is to symbolize this and use a symbol that represents the same device. So one thing that we can do is, for example, put a box and say this box is a light bulb. Now, in the electrical domain, there are two connections to the light bulb, as you may know. And now, this representation with just the box and with two connections is much easier than drawing the whole thing. So from now on, every time that we want to represent an electrical device or electrical component, we're going to use a box and connections to it. And then beyond that, depending on what that device is or how physically it operates, we can actually do more labeling, more detailed labeling that would tell us what that component is. So in this case, I wrote light bulb, but we can actually symbolize that, and instead of using characters, we can actually use a symbol for the same component. As an example, for the most purposes, the same light bulb could actually be represented with a simple electrical resistance, and this is the symbol that is normally used for electrical resistance. So you can see the progress of going from a schematic that kind of resembles the actual device to a representation that describes with letters what that is, and to just a simple symbol that represents the functionality in the physics domain. Now, that said, in the electrical domain, we deal with two physical quantity. One is called a voltage or potential, and the other one potential difference, and the other one is the current. So let's quickly define what that is. So here you want to pay real good attention. Everything starts with an electron. So inside every atom, we have a nucleus with positively charged protons, and these quantum mechanical particles that we call them electrons that are negatively charged around the nucleus. Now, as we know, positive and a negative charge, they attract each other. And the reason these electrons are actually kind of bound to the periphery of the nucleus is because of that electrostatic force that is between the two. Given that, if you have positive and negative charge, because there's an electrostatic force between them, if you want to move these two away from each other, you actually have to apply force, and in other words, you inject energy in the system. So as you separate the two charges, you inject energy in the system, and this energy is going to be preserved in the system in the form of potential energy. Now, if you take the energy that we discuss in this system, the potential energy that we discuss in the system, and take the derivative of this energy with respect to the unit of charge, this is the definition of the quantity voltage. Okay, so let's just quickly review that. You have positive and negative charge. You inject energy in the system. The energy of the system changes. In this case, if you're separating the two from each other, increases. And if you take that change in the energy and take a derivative of that with respect to the unit of charge, what you get is called a potential. Okay, so now electrical potential. So this electrical potential, it basically represents the rate at which the energy of the system changes per unit of charge. Now, you have to keep in mind that the potential, the way that we discussed it, is actually it's a differential concept, meaning that you always measure the potential with respect to a reference. What does that mean? Let me actually give you an example, an analogous to this, that is more, it's easier to understand for us. So think of Earth and something on top, and the gravity, the force gravity. As you move something that is close to the Earth, so this is the Earth, and this is another mass M1. If you want to move mass M1 away from the Earth, you have to inject energy into this, and that energy actually gets conserved in the system in the form of potential energy, as you know. And the further you move M from the Earth, the mass M from the Earth, the amount of that energy increases. The potential energy increases. Now, the amount of that energy really, or what you have in here is every time that you want to measure that potential, you have to know where your zero potential per se is. For example, if you have basically different levels on Earth, right, in terms of height. Now, the energy of this mass, potential energy, with respect to the top of this basically raised region is something, and that's different than the amount of energy with respect to the lower part of this raised area on Earth. So if you say my potential, once this ball reaches down here, my potential energy is 0. In other words, you say this is my reference, then everything above that is a positive energy. Once you reach that height, that's your 0 energy, and anything below that, it kind of is negative with respect to that. But if that's your 0, then you have a different, even though when you touch that level, you still have some potential energy in that mass. Same with here, with electrons. So with the electrons, or positive charge and negative charge. So you always have to have a reference for what is your 0 potential, electrical potential. That's a very fundamental concept that you always have to remember. And with that comes the differential definition of voltage. So if you take the potential on one side, or at a certain node in a circuit, or a certain node in a component, and you assume that the reference for that potential is the other side of the component, you can actually take the difference between the two potentials and define something that we call a voltage. Okay, So voltage of that potential. So the voltage for a component is basically the difference between the potential on this side and the potential on the other side. So we can actually define this as the potential V plus, and then the other and potential V minus, and then we say V, the potential across, or the voltage across, is equal to V plus minus V minus. This is very important to keep in mind. A lot of times the two concepts get confused. The potential difference and the voltage are the same thing, but the potential on each node is different. Sometimes people assume, for example, that V plus is the same as V. It's not. The voltage across is equal to the potential on one side subtracted from the potential on the other side of the device. Now, because of this potential difference, and if there is a potential difference, there would be a force that is applied to the charges. Why is that? You can actually go back to this here. Assuming that there's a potential difference, meaning that there is energy conserved in the system, and this energy only would go away if the two charges basically are exactly on top of each other, at which point there is no energy. Now, if there is energy, potential energy, electrical potential energy in the system, then there would be a force that is attracting the two. This is the force that we apply to move them away from each other, but then there is, now as a result, there would be an electrostatic force that would actually attract them to each other. And therefore, if you apply a potential difference, in other words, if there is electrical potential energy stored in the system, then there would be a force applied to the charge that would cause the electrical charge to move, right? Generally speaking, it would push the electrical charge, and a lot of times that push or pull is going to cause the electrical charge to move. Now, if you, in a device, you get the electrical charge, which is the electron, start moving through, then you can define this other quantity that is important for us, which is the derivative of the charge that is moving, passing through a cross-section with respect to the time. So derivative of charge passing through a cross-section with respect to time, and you define that as the current. Now, this is usually the positive charge with the definition that we have, the standard definition that comes from way before. But since the charge that actually moves in all the systems, electrical devices, are electrons, the direction that we assume the current is moving is actually the opposite of the direction that the electrons are moving. And this actually causes some confusion. Unfortunately, at the time that this concept was defined, it was taught that the charge as the current is passed is actually flown as a result of positive charge moving in devices, and later on it was corrected in a sense that without we know that it's the electron that moves and the electron has a negative charge, but that definition based on the movement of the positive charge kind of got stuck, and you always have to just remind yourself that the direction that we define the current is moving is actually the opposite of the direction that the electrons are moving. And the electrons move from the lower potential to a higher potential, or in other words, the positive charge moves from the higher potential toward the lower potential. I'm going to finish this discussion by now showing you something Interesting. So if, in other words, to explain to you why these two definitions matter. What really matters in all systems, and this is a very general statement, is how energy transfers, how energy is generated, and how energy is consumed. So again, in all systems, what we really deeply care about is the generation, transmission, transformation, and consumption of energy. That's fundamentally what we care about. Now, you can see here that if I take voltage and multiply it by the current, by definition, what I'm doing is taking derivative of energy with respect to charge and then multiplying it by derivative of charge with respect to time, which what's going to be left is the derivative of energy with respect to time. And that definition should be actually familiar to you. Derivative of energy with respect to time is power. So that's a really good motivation for these two definitions to be of fundamental importance for us. That's why we really deeply care about the voltages and currents in all the devices that we have in electrical circuits, because once we know the voltage across, the potential difference across a component, and the current that is passing through the component, we can actually multiply the two by each other and calculate the power that is in that component. And power being energy consumption or generation per unit of time, that's fundamentally what we care about. With that, I'm going to stop, and we're going to continue in the next lecture. Thank you.